tension members. So this time we will now discuss how to analyze and design what we call now compression members. Okay, so here are the intended learning outcomes for this module. So at the end of the module, the students will be able to describe and distinguish compression members in a structure, enumerate and explain the limit states that govern in analysis and design of structural steel compression members, and analyze and design those members considering strength and serviceability requirements in accordance to the relevant code provisions. Okay. So module topics. So topics in this module include the definition and examples of compression members, the Euler buckling theory. So I think for today I will only discuss up to this point. Okay, the Euler buckling theory. Next, we will have the inelastic buckling theory, local buckling, and analysis and design of compression members. Okay, so without further ado, let us start. Okay, so what are compression members? So compression members are structural elements that are subjected to axial compressive forces. So some examples of compression members are truss members, columns, and frame braces. So as we see in the screen right here, so if a truss is subjected to load, some of the members will act in tension, like we have discussed last time. And some other members may act under compression. So in this particular truss here, if it is subjected to this loading, these three members in no, the red members here, so the two top chords and this diagonal members right here are subjected to compression. Okay. Then another example are columns. Okay. So and upside, so because it supports your beam and your beams and your floor systems. Okay. And then we have also the braces. No? So for example, you apply a lateral load here. What happens is this brace here will be subjected to tension, to compression, and this brace here will be subjected to tension. Okay. So here are some examples of compression members. Okay. So in analysis and design of compression members, so in this module, we will be focusing on columns, okay? Especially columns. The following member limit states are to be considered. So the two limit states that we consider are what we call general buckling and local buckling. So what's the main difference between the two? So when we say general buckling, it is the instability of the member itself due to the compression load. So let's have this column right here. So if you subject it to compression loads, if it is, so from what we know in structural theory, it should only shorten, right? So that's what we expect. However, in some cases, especially if it is slender, so we will define the slenderness of a member. Okay, no? So in some cases, if you apply compression here, instead of shortening, we will actually encounter some sort of bending, either in this direction or the other direction, the out of taper direction. Okay, so that deflection right there is what we call general buckling. However, general buckling is not solely signified by lateral deflection. Twisting may also occur in this member. So that's what we call torsional. So if buckling is signified by lateral deflection, so if it just deflects, that's what we call flexural buckling. While if it twists, that's what we call torsional buckling. Okay. So the point here is general buckling occurs globally to the member itself, on the member itself. while local buckling, it is the instability of the section components of the member. In this case, for example, we apply a load here. What happens is that it may not deflect. It may not buckle generally. General buckling may not occur. However, the flanges and the web of the member may actually deform or warp. So that's what we call local buckling. So local buckling is signified by the deflection of its section components. Okay. Do you have any questions so far? So I guess none so far. Okay. So again, we have the compression members. We have some examples right here. Where do we see them? And then the two main limit states that we consider in analysis and design of compression members, we have general buckling and we have local buckling. So for this lecture, we will only be discussing right now general buckling. Okay. So before we proceed to the Euler buckling theory itself, so first let's expound a bit what general buckling is. Okay. So general buckling is the instability of the member due to applied axial compressive load. So just like what we have described last time. General buckling is classified into three types. So we have flexural buckling, torsional buckling, and flexural torsional buckling. So how do we differentiate the three? So flexural buckling is characterized by the lateral bending of the member. So here in this in figure A, we see that as you apply the compression load, the member just deflects. So if it just deflects, that's what we call flexural buckling. Next, we have torsional buckling. It is characterized by twisting of the member. So for example, this member right here, if it is subjected to compression forces, what happens, especially if your section is some sort of a crucifix, no, or a cross, is that it will just twist instead of bend. Okay, so that may also occur. So that's what we call torsional buckling. And then the last one, it is pretty much the combination of these two buckling modes. So that's what we call flexural torsional buckling. So it is characterized by both lateral bending and twisting of the member. So we have this, so it deflects, and at the same time it sort of so if it deflects, the section here must remain upright like this one. Okay, however, so some twisting is also evident here. So that's why we classify this particular buckling here as flexural torsional buckling. Okay. So in our module here, we will only be focusing more on flexural buckling. Precisely because the mathematics behind the torsional and the flexural torsional buckling are more complicated. No? So we will not be discussing this. Okay. So let us proceed. So the general concept behind flexural buckling is governed by the so-called Euler buckling theory. Okay. So there you go. No? So let's assume that we have a simply supported column, no, subjected to compression forces like this one. Okay. So Euler buckling theory forms the basis for studying or considering the flexural buckling behavior of compression members. So before we proceed with the theory itself, what are the assumptions that we should make, that we should form for the theory to be valid? So first, the material is homogeneous, meaning the material properties at the same at all parts of the member. Okay. Next, there are no initial or residual stresses introduced to the member. So, no thermal stresses, no initial loads, etc. Okay, so next, the member is perfectly straight and prismatic. So, the plumpness is okay. When we say prismatic, the cross section is pretty much constant. No? Same shape, same dimensions, same cross-sectional area, and other section properties. Okay. The axial compressive load acts through the centroid of the cross-section prior to bending. So the reason for this is to prevent the development of additional moments. So if the load does not act through the centroid, what happens is that uh, eccentricity is present. So, and that eccentricity will cause uh, moments at the ends of the column. No? So, meaning, it will most certainly deflect, no? Kung ganun ang mangyayari. Okay, so we only want the deflection caused by the load itself. We do not want the deflection caused by the eccentricity. Okay. Next, end conditions are ideal. So yung support natin, we consider them to be perfect. Okay, so in our case, for now, in Euler buckling theory, we will only be considering pin-pin connections. Okay, so simply supported muna tayo. Okay, next, small deflection theory of ordinary bending is applicable and shear effects are neglected. So plane sections remain plane. The deflection is significant. The measurement of deflection is significantly smaller compared to its length. Okay, so elastic flexure theory holds true. And lastly, twisting or distortion of cross-section does not occur. Okay, so no torsion, no local buckling. Okay, so only the load will cause stressing of the member. Okay, saglit lang. All right, so let us proceed. Okay. So the derivation of the formulas here, I will not discuss it anymore now since wala pa rin akong graphic tablet hanggang ngayon. Okay. So I cannot discuss the derivation so far. So I will just point you out where you can read them. So you just have to read them. Kung may questions kayo, just present it in the discussion thread. Okay. So I will not discuss the derivation anymore. No? So there you go. Okay. So assuming pin connections at both ends. So the derivation is at chapter 3. Chapter 3. I don't know. No? So we may correct this one. So maybe chapter 4 to or something. No? So just just verify this one. Okay. So assuming pin connections on both ends, the critical load to be applied. So here, a differential equation may be derived from here. So from that differential equation, so actually para lang siyang yung sa bending ng beam. Doon lang rin siya nanggaling halos. Okay. So from there, you solve the differential equation and then you come up with the maximum load that the column will be able to resist prior to buckling, without buckling. Okay. So based from that differential equation, the critical load to be applied to the compression member to prevent buckling is this one. Okay. So PCR is the critical buckling load. So when we say load, it is in kilonewtons or in keps. So E is the modulus of elasticity, A is the cross section, L is the length of the member, R is the radius of gyration of the member. Now, if you recall, the a particular steel section has two radii of gyration. Okay, so one in the x-axis, one in the y-axis. So which one would you use? So in this particular case, no, it depends on the direction of buckling that you consider. So if the buckling occurs about the x-axis, so it bends about the x-axis. Okay, so meaning you use Rx. Okay, but if you consider buckling about the y direction, okay, so you use Ry. Okay, so it depends on which buckling direction do you are you considering. Okay, so there you go. This is the critical buckling load. Okay, however, this one is only valid for simply supported columns, so pin connection or pin roller connection. Okay, however, what if the support conditions are different? So the same form the same form of the formula will be adopted now. However, the only addition here is what we call the K. K is what we call the effective length factor of the column. And the term KL here is what we call the effective length of the member. So why do we say effective length? If we observe this, no, particularly this 4, A, B, D, and E. So for fix, actually this one is a bit wrong, okay? So let me just illustrate, okay? Do you see the whiteboard? Do you see yung whiteboard natin? Okay. So for example, we have a column right here, okay? Again, I apologize for the drawing. No? I do not have the tablet yet. No? So, ito yung column natin. No? So, assume na lang natin na perfectly straight to. So, let's consider 4 columns. This one is a pin. This one, say this one is fix. This one is fix pin. And say this one is fix free. Okay. So for pin-pin connection, for simply supported connections, the expected buckling shape would be this one, like this one. Okay. For fixed peaks, we know that both the slope and the deflection at ends is 0. So meaning, we cannot expect that there will be some slope here. So we expect that the deflection of the column is pretty much like this. Okay. So let me show it more clearly. Okay. Here, the slope again is 0 here, but here there's no zero slope. So meaning the deflection is like this. Okay. And then here we consider the deflection to be like like this. Okay. So we consider that there are compressive loads applied here. Okay. So in this case, for pin-pin connection, the when we say effective length, or in the so we call them effective length, or in some books we call them unbraced length. Okay. So here, so the effective length or the unbraced length is actually the length of the column that experiences significant deflections. So in this particular case, for simply supported columns, the effective length of the column is just the same as its true length. Okay. So in this particular case, the effective length factor is just 1, because this one is defined as K times L, where L is the length of the column. Okay. For fix, it is derived the uh, that the effective length of the column in fix condition is just half of the length. Okay. So it was mathematically derived that the effective length of a fixed column is just half of the length of the column. So the effective length factor for this particular column is 0.5. In this case, we just have to combine the two. Okay. So here, so the effective length here is approximately at around 70% of the length. Okay, so the K here in this particular case is 0.7. Okay, in other books they consider this to be 0.75, but then we stick with the more conservative value. That's why 0.7. In this particular case, the entire length is has deflected. However, the deflection does not end. We want the deflection to close. So what happens is, for example, we have this column here. We actually put a reflection line here. Okay. So that there is reflection. Okay. Then we consider this to be deflected like this. So if we actually trace its reflection, it will be like this one. And this one, as we know, is the length of the column. So this one is also the length of the column. So meaning, the actual effective length of a fixed free column is twice the length of the column. That's why in this case, the effective length factor that we use is 2. Okay, so there you go. So these are the effective length factors. No? considering different end conditions. Okay? Any questions so far? Any questions? So wala no question. So malinaw tayo dito Sige. So let me go back with our screen. All right. So the theoretical values dun siya nanggaling, no? Dun sa pag-trace ng actual buckled shape ng column natin. So however, we do not use theoretical values. We actually use the recommended design values, no? Para for more conservative design. Okay, so if you observe, in most cases mataas yung mas mataas yung nire-recommend na K value because the higher the K value, the lower the load. Okay? So mas conservative ibig sabihin. Okay? So this particular table here that I showed, that I'm showing right now, is actually can actually be seen from page 277 of the ASEP Steel Handbook. Okay? So in some cases we can use this one. Okay? So yun lang, no? Then another note for this particular term right here, the term KL over R is what we call the slenderness ratio. Okay? So itong term na to, yung KL over R. So this parameter is used to determine the susceptibility of a compression member to flexural buckling. So how do we know if a column is prone to buckling or not? So we can actually take a look at the slenderness ratio. So if the slenderness ratio is very low, so if this is very low, meaning the load that you can apply for it to buckle is very high. Tama? So lower slenderness ratio indicates higher critical buckling load, thus making the member less susceptible to buckling. The same thing so conversely, kapag mataas yung slenderness ratio, if the slenderness ratio is high, it indicates lower critical buckling load. So based on this formula, so meaning the member is more susceptible to buckling. Okay, so that's one parameter that we use to evaluate the slenderness or the susceptibility of a column to buckling. So that's why, how do we actually design columns? So two ways. First, you enlarge the first you maintain a short length for the column. Okay? So para mapababa natin slenderness ratio. Okay? So the point here in designing columns is that you want the slenderness ratio to be as low as possible. So it's either you shorten the length, however, it is not always done. Bakit? Because of architectural requirements. You don't really want the since we follow the architectural dimensions, you cannot just lower the length or shorten the column. Okay, so the other method that you can actually do to lower the slenderness ratio is to enlarge the section. Okay, enlarge the section. So if you enlarge the section properties will consequently become higher. So the cross-sectional area, the radius of gyration, the moments of inertia, etc. Okay, so this one is important, the slenderness factor, the slenderness ratio. Okay, So in analysis and design of compression members, the recommended design values for effective length factor should be used. So just like I told you earlier, we do not use the theoretical values. We want some conservativeness when it comes to design. So that's why we use the recommended design values. Okay? For members with bracing at some points along it, the effective length to be used should whichever critical be equal to either. So the distance from an end brace to the end support to the nearest brace, or the distance between braces. So I will show this a bit later, no? Kung what if there is bracing. Okay, so just some just some note, no. When we say bracing, it you actually prevent the deflection at that point, no. Bine-brace mo siya from deflection. So what does it? So what is the effect of bracing on the columns? The column shape will be different. The buckling shape will be different. Okay. So later we will discuss how does it actually affect the excuse me, the how does it affect the buckling shape of the column. Okay. So right. So let's leave it. Let's leave this one for now. Okay. It should also be noted that flexural buckling may occur in any of the two directions, whether about the strong or the major axis of the member. So when we say strong or major axis, that's the axis where there is greater moment of inertia. In most sections, in W sections or I sections that we have in steel, the the IX or yung sa X axis usually yung major axis natin. And yung weak or yung minor axis is yung about the Y, because it has lesser section properties. Okay. So the slenderness ratio of a member have two values. One for the strong axis and the other for the weak axis. Okay. So more information. So may dalawang slenderness ratio palagi ang column. About the X and about the Y. Okay. So which one will, how do you know at which direction will the column buckle? Kung saan doon yung may mas malaking slenderness ratio, that's the point kung saan that's the expected direction of buckling. Doon siya mag-occur first. Kasi yun yung mas malaking slenderness ratio. Meaning, mas susceptible siya on buckling at about that direction. Okay? Any questions? Okay, so none so far. So let me just go with this topic 3.10. Okay, so we have 3 videos here. So first, I'll show you the one about the Euler buckling. So you don't have to worry about the audio, no? Walang audio tong videos natin. Okay, so let me enlarge this one. Alright, so let me show the video. Buckling happens when a member becomes unstable due to slenderness. So this is the so this one, ito yung if you plot yung if you plot the Euler buckling formula, okay? So ito yung load, ito yung slenderness ratio. This is the expected shape. Okay? Especially itong nandito at this latter part. Ito medyo iba to. So we will discuss it at a later date bakit naging ganito. So usually kapag Euler buckling, it's more in the form of in some sort of a parabola, parang ganun. Kasi to the second degree kaso nasa denominator, no? So it's some sort of a curve, no? Like this one. Okay? So eto, hindi talaga siya kasama do sa Euler curve natin. So actually paganto siya. Okay? Pa-upward siya as you go with the lower slenderness ratio. Okay? So let me proceed. All right. So yung Euler buckling formula natin, so I pause it for a while now. So the assumption in there is that elastic yung buckling mo. So at this portion here, it obeys the Euler buckling theory. Okay, so that's why yung plot niya dito, nag-fit siya dun sa Euler buckling formula natin. Okay? Alright, so they showed what buckling looks like. So yan. So elastic buckling yung Euler buckling natin. Okay? So let's just skip this one. No? So next time I will explain kung ano tong portion na to. So the important thing is this one. Okay? Right, so do you have any questions about the first video so far? So it just illustrates yung Euler buckling. No? Right, so next we have the slenderness ratio. Okay, so medyo nagloloko yung video. Okay. So yes, sorry. So it highlights the importance of the slenderness ratio. Okay. So we also have yung bracing. So ito no. Ito yung bracing na sinasabi natin. Yun. So if you observe, the effect of the bracing is that it changes the expected buckling shape. Okay? So kapag walang bracing sa gitna, it will deflect like this. However, if there is bracing, pipigilan niya yung buckling at this point. So what happens is that there will be buckling at this portion and there will be buckling in the opposite direction here. Okay? So typical buckling is calculated for the minor axis. However, if the minor axis of a column is braced, buckling may occur on the major axis. So this second statement, I will illustrate this later on. Pero considering na walang buckling, we can expect na sa minor axis siya una mag-occur kasi nandun yung mas maliit na section properties. No? So like what is shown earlier at the earlier part, mas nag-buckle yung may maliit na section kaysa dun sa mas malaking section. Okay? So dito, it just illustrates na yung bracing mo may occur in both directions or only in one direction. So in that case, you still need to determine the slenderness ratio in both directions. Okay? And this one, yung effect naman ng support conditions mo. Yun yung tinitingnan natin. Right? So this one, like I have drawn earlier. So kapag meron kang fixed support, some part of the column is has a negligible slope or negligible deflection. That's why we do not consider it part of the effective length of the column. So mini-measure lang natin siya from here to here, or in this case from here to here only. Okay? So yun yung effective. So that's why we have the so-called effective length factor. Right, so there you go. So in-explain lang niya yung slenderness, how to what are the factors that affect the slenderness ratio of a column. Okay? So the other video, tsaka ko na ito ipapakita no, about the local buckling. Okay? So do you have any questions so far? Any questions? Alright, so no